Hi, folks. This is the lab in week 4, and here is the item on the agenda today. I'm going to be doing two problems for you. They Remember, we're working with assemblies right now. The first one is called the shaft bearing assembly, and then once I do that, I'm going to come and do a shrink fit problem, which is actually uh, very similar to the activity in either the morning or the afternoon class. I think it's the afternoon class that you have to do. Okay, so let's go to the problem that we're going to do. This is called a shaft bearing assembly because it looks like something is stuck. This shaft is stuck inside of these two supports, which are called bearings. Okay, and it's made of aluminum, and I'm assuming that there's contact between these two faces. Now, remember, if this object was casted as it is that you see, then it's foolish to solve this problem as an assembly, because if it's casted, it's all one piece. You solve it as a part. But if you wanted to do it as an assembly, what you can do is you create two bearings and put this shaft in it, and then create a connection between the shaft and the bearing here and there, and call that thing a fasten connection, which it behaves as if this whole thing was uh, casted or machined the way it is. That's not what we're talking about. We have these two bearings, we buy a shaft and stick the shaft inside of that bearing and do something with it. Now, the only thing is that it says that the downward load of 1,000 pounds, the only difference difference with the problem that I'm going to do here, this drawing, I put stand there so that I can put the 1,000 pound on that stand. Okay, so my shaft doesn't quite look like that, but it looks something with a stand here where we're going to put the 1,000 pound or 1,000 pound on it. I'm going to do the problem with and without planes of symmetry. Okay, so let me assume we'll get to it in a minute. We will get to it in a minute. I don't want to rush and give away the stuff that I'm going to do. All right, so let's go ahead and make it. Uh, First of all, it's a product, it's an assembly. Immediately I save this thing, file, save management, save as. I have a folder here on my desktop. Okay, desktop. We're going to create a folder. I say shaft bearing assembly. Shaft bearing assembly. Now we put everything in there. All right. Let me insert the first part. I'll do the bearing first. Insert new part in there. And I'm going to call this thing bearing. Right click properties. Now notice that these two bearings are identical. So it's foolish to make two of them. You can make one. And then if you insist, copy and paste it to get a second one. Or once you create one, you save it and then insert an existing component. So that's the pathway that I'm going to take. Okay, I'm not going to copy and paste just like I did the problem on Tuesday. I think I did the problem on Tuesday, where we have the block which were being pulled by two pins. Okay, so let me do this thing. Properties. I'll call it bearing. All right, this is the instance name, and here is the part name, bearing. Now we can make it. So I'm going to double click on this to go into part design, and on that top plane or on that vertical plane, I will sketch something that resembles what I want to do. We'll put dimensions in a minute. Okay. First of all, I want this thing to be nice and symmetric. So for example, I can select this, either put that center on that vertical axis or select this, control that, control the middle axis, and I'm going to make it equidistant or symmetry. Okay. automatically it puts that center on there. And let's dimension these things now. So this is 2. This is 2 inches. And so is this one. 2 inches. Obviously, that makes this radius 1. And then I'm going to make a circle there with radius 0.5. Okay, so dimension, actually diameter 0.5. All right. Good. Let me just check. See, it looks like actually, yeah, diameter 1. We'll make it like that. Diameter 1. All right. Exit. And I'm going to pad it by 1 inch. There we are. This entire assembly is made of aluminum, so at the very end I can put the material on the aluminum. I go all the way to the top, all the way to the top. I'm at the assembly level and click on the floppy. So it's going to save this part in it. Now that I saved it, what I can say is insert existing component. In there, it says where is it? Well, I put my stuff in this folder, shaft bearing assembly, click the bearing, and I say okay, and they're both sitting on top of each other. So depending on how you were taught in your first CATIA class, you can move these things apart. I'm going to use manipulate here and say move in the direction Y. You can see that they're sitting on top of each other. You do it any way you want. Just make sure you can do the prop. Now, click on. Now remember, I could have copied and pasted it in product. That's fine. But the amount of storage, hard disk storage that does is different from inserting existing components. For example, if you have 100 of these, copying and pasting 100 times is going to be a lot more resource intensive than just making one and inserting multiple instances of that, which incidentally can be done with the multi-instantiation. I'm not going to do that. So now we're going to insert our shaft. Insert a new part. Insert a new part in there. And I'm going to call this thing, say no, and I'm going to call this thing right-click properties, shaft. So this is the instance name, shaft, and this is the part name, shaft. All right, let's go make it. Double-click on the shaft, on a convenient plane, on that plane that's convenient for me, use sketch. Actually, let me exit that. So what I'm going to do is there's a shaft. So this plane, see this plane? Actually, it really doesn't matter. On that plane, that's fine. I can do it like that. So I want to draw a circle that size. So what is better than projecting that circle on it? Okay, there we are. Okay, and then exit and pad it by 10 inches. Actually, what I'm going to do is this. I'm going to double click on this thing, make 5 inches, and go mirror extend. There is a reason, because remember I was talking about making a stand here. I do it symmetrically so that I know exactly where it is. So on that plane, on that horizontal plane, I will sketch. All right. So there is my stand. I'll make it circular in shape. Because of what I did, I made my job easier so that I know there's 5 inches that way, 5 inches that way. So that, unfortunately, is not how I was about to do that. So Control Z, get rid of that. I'll tell you what. Okay, good. Unfortunately, because of what I did, I don't have a plane exactly in the middle of these two. Exactly in the middle. So what I'm going to do, I will say create a plane. I increase the amount of work that I have to do by not paying attention to the plan. So plane, uh, I want to get a point exactly in the middle here. Okay. So let me do the following. I have made my work so much harder here. So let me do let me do the following. So create a point. Okay, create a point, point and direction. Well, actually, let me say between this end and that end. Uh, Not on a plane. Between this end and that end. Between Okay, so what I'm going to do is say between this point, and for that point, I'm going to say create a point, center of a circle, this one. Since it doesn't matter to me how that stand is created, why don't I do the following to do that? Let me first of all move this guy so that either hide it or remove it so I don't see it. It's not blocking my view. So I'm going to manipulate, translating the direction Y so it goes out of the way. Now, on that, what I'm going to do is create a plane 5 inches offset from this side. So here is the reference elements. Let me find the reference elements right there. uh, Actually, it must be hiding behind that. Oh, where you make points and lines and planes. Uh, okay, oh, that's because I'm in product. So let me go to this shaft first. Let me go to the shaft if I'm not already there. Here is a plane and offset from this surface in the other direction by 5 inches. So it places right in the middle. And on that plane, I will sketch. So something perhaps like this. As I said, the shape of this doesn't matter because I want to make stand, create a feature there. Uh, Actually, let me do the following. We move it a little bit up. Where is that? Okay, so I'll draw it like this. Yep. Maybe move it a little bit further down. Exit. And then I pad it. Maybe symmetrically by maybe 0.5. See how it looks like so. This could have been any other shape, so I'm going to place my load here. In the past few years, I drew a circle here and padded it down, etc. But that's okay. So you go all the way to the top, all the way to the top, save everything in that folder, and now we're going to assemble it. So always fix something when you're doing constraints. So let's fix that guy. So everything else moves but this. So coincidence between this axis and that axis, that's already coincident, no problem. And coincidence between, let's say, this plane and that plane. There we are. Do the same thing on this side, although I will do the axis, but it's unnecessary because these are already coincident because of translation. And then coincidence between this this plane and that plane, and we say okay. Good. So let's save everything all the way to the top. Apply material to it too. Make everything out of aluminum. I think what the problem said, aluminum, yeah. And then we say okay. Good. Now, save everything. Because I'm at the product level, I click on the floppy, everything is done at the same time. So now we're going to go to generative structure analysis. CATIA sees 3 parts in there, and it will mesh each one of them. There's the bearing, there's a bearing, and there's a shaft. Now, this is too big, so I'm going to make this thing a little bit smaller. For the shaft, I'm going to make it smaller. I'll make it point, maybe 1. Okay. All right, change the rendering so that you can see it better. There we are. Anything that you don't like, you can hide. So for example, these guys, if you don't like, you can select them and hide them and deactivate the mesh to proceed with the rest of the problem. All right, I'm not using any planes of symmetry here. Although, you see, these bottoms are both clamped and I'm applying a pressure or a force of 2000 on that stand. So definitely YZ is a plane of symmetry. Whether XZ is a plane of symmetry or not depend on certain things that we're going to discuss. Okay. All right. So first of all, the bottom of this is clamped, and that one is clamped. Okay. Good. And we're going to put a force of 2,000 pounds on this. Okay. That's what the problem said. Or 1,000 pounds on that stand. So let me apply a total force. This is pressure. I don't want to apply pressure. Force 1,000 pounds in the direction Z minus 1,000. Okay, good. Let us save our analysis. If this thing, the support is, yeah. If this thing doesn't close this because I already put it in there, it could be that there's something sticky with your keypad or something like that. Just cancel that. The first one is still there. You can see that. Okay? You see? Good. Now, let's save our analysis. File, save management. Here's the analysis. Save as. That same folder that I got shaft bearing assembly, analysis. And I'm going to say OK and close. Good. Now, if I run, it's going to bomb out. And let's do it and find out what the issue is because we're trying to learn how things are going to work. Bombed out. Do you know why? Plot the deformation and animate. You can see that these guys are not seeing each other. The bearing has no idea there's a shaft there. Shaft has no idea there is a bearing there. So they penetrate through each other. So let me deactivate this plot and create a connection between the surface of the shaft and the surface of the 2 holes which says contact. So let me do it like that. Connection. It's right here. As soon as you do that, a connection branch is created. For the first component, surface of the shaft. For the second component, hide the shaft, surface of this hole, and another one on this side. Another connection. It's a good idea to name these things, but I didn't. So the surface of the hole, the order does not matter. So I can select the surface of the shaft. The order doesn't matter. And if you want, you can bring this in the front. There we are. So 2 connections I've created. This one for the left side, this one for the right side. All right. Now, what kind of connection are they? Are these glued together or fastened together or perfectly welded together? If the answer is yes, it's as if we had basically something machined like that and, we're loading it. But that's not what I want. I said that I buy this shaft and stick it into those holes, okay? So it has to be contact. So go find a face-face connection. Remember there? Connection properties, the first set of the first toolbar. This is fasten. Oh, sorry, this third one is fasten. I don't want it. Contact. You click on contact. You select this guy. Say, okay, don't worry about these boxes. Don't do that until you are a bit more familiar with the stuff. Notice that it put contact icon here. It looks like two things on top of each other. Good. Save it and run it and watch it fail again. The reason it takes a little bit longer than usual is I'm taking unnecessarily a very small element. Parabolic, very small. There's a lot of elements there. In fact, if I made it linear, it runs a lot faster. And maybe I should do that next time, next time that I run it. Okay, good. Anyway, it failed. We see that. Now, do we know why? Well, let's plot the deformation. There we are. And animate it. Change the scale so that you can see it better. Reset it. There. And animate it. You see, it's not penetrating the bearing, but it's sliding out. So the question is, when I bought this thing from store and stuck it in there, aside from friction, what if there was no friction, what would it prevent from sliding out? Well, one option is to go and say, okay, let me first of all deactivate this. One option to go and say, you know what? I'm going to weld the edge of this bearing to the edge of the shaft. Welded. If it's welded, then it cannot just slide out. So let's do that. Create a connection, and I'll call this thing left welding, which means left bearing. Okay, for connections, the first connection, I'm going to hide the bearing, and for the first component, I select this edge. And for the second component, I select the edge of the bearing, which is hiding right now. Let me bring this in the front, hide the shaft. If there's any possibility of accidentally picking that. So I want, let me see. I want this edge, another edge. All right. So we created a connection which was called left welding. Now, how do we say it's kind of welded together, glued together? We make that thing a fastened connection. See that? This was contact. This is fastened. And select that. It puts kind of a fastener sign here. That doesn't mean it's a fastener, but let's try to run it now. Let's bring this thing out of the hiding. Go there. Save it and run it. So just wait. Oh, I should have changed the element type to linear to go faster, but anyway, we'll do it. Let me cancel that. Let me go here, make this thing linear so it runs faster. We don't have to sit there and wait. Everything is linear. Okay, now we're done. It's going to be a lot faster. There. It didn't bomb out. How does it look when it deforms? First of all, let me plot the deformation. But if I cannot see much, then I should reset the scale. Default. There we are, isn't it? That's the way it should be. Now notice that because we said that this left edge is welded to that, they go together. But if you go on the right-hand side, you can see it's sliding out because it's not welded. Now, this is why I said whether the XZ plane is a plane of symmetry depend on what you have done. If you have not welded here, XZ is not a plane of symmetry, and the only thing is YZ. Okay. Now, if I go and create another, close that, deactivate this plot. If I go and create another connection on this side, edge to edge, and make it welded, you will see that this does not slide out, and then this is going to be a plane of symmetry. So I'm going to repeat. So I'm just not going to weld this side. I'm just going to weld the left side. Think about it like that. I'm going to repeat this problem with symmetry though. Okay, so let me first save the analysis. Okay. All right. What I'm going to do, I'm going to go to the assembly design and cut this. You can go to the individual, you can, oops, let go. You can go to the individual parts and cut it, or you can use the split that's in the assembly and cut them at the same time. You click on it, and it says cut the stuff with this plane, and it says when you cut it with this plane, there are 3 parts that are affected. You want all of them to be affected, or some of them? I say yes, and we say okay, and it says which side you want, this side or that side. If you want the other side, you could have picked it there. But anyway, there we are. So now we have cut it, okay? So let me do the following. Let me go back to the analysis. Let me go back to the analysis. All right. And just so that you see it again, you know what? I'm going to actually let me save the part. If I have not done it, let me save the part or the product actually. We did it. I'm going to get out of this. All right. And we're going to try another analysis. This is a round 2, so you get to see it again. All right. So let's go ahead to analysis and simulation, generative structure analysis. Remember, I changed the size of this thing. I changed it to maybe 0.1. Everything is linear. Oops, which one was it? Control Z. I picked the wrong one. This is the one I wanted. 0.1. Linear now. Okay, so that it runs faster. If you want to see the mesh, it's right there. It's the same mesh, but it's linear. Okay, let me deactivate that. And let's go ahead and put the surface sliders there. So where is the surface slider? Where are the restraints? Oh, you know what? I accidentally deleted the static step. So I can do that. Insert, static case. You say fine. There we are. Now these things are back. So surface slider, select this and that and that, that one and that one. And this was because of plane symmetry. If you see, already it did it, but I have a kind of sticky key on my laptop, so it does that. Then it's still waiting for the second slider surface, which I don't want. It's right here. You can see that. I think it has to do with my mouse. I've got to change the battery in it or get a better mouse. I don't know. So the bottom of these two are clamped. This is clamped, and that is clamped. Okay. All right. Now we have to create our connections. So connection. First, let's do the contact connection between this face. Hide that. Which one did I pick? Yeah. Hide the shaft. For the second component, that face. Say okay. All right, and do another one. This face, again, the order doesn't matter. For the second component, I select the surface of the shaft. Bring this thing in the front. Okay, there we are. These are created, and these are both going to be contact, right? So we do contact connection. We've done it already twice. Contact, this is going to be contact. Another one is going to be contact. The second one is going to be contact. And if it doesn't code, just cancel it. It's already did it. And then I don't want this thing to slide out, so I create a connection between the edge and edge and make that welded. So let me create a connection, another connection. I'll call it welding, edge welding, so that you recognize that. All right. First component, zoom in, hide the bearing, select the edge of the shaft. Second component, select the edge of the bearing right there. And bring this in the front if you want to see it. Say OK. There it is. And we make that thing fasten. So fasten is the third one from the left. This one is going to be fastened. It kind of puts a fastener sign there. And then we put a load here. Do not forget to take half of this. Not 1,000 minus 500. And then we say OK. Save our analysis. File, save management, analysis, save as. There was already something there, but I don't want to. I want a new one. Say with symmetry. Okay. Say okay. Say okay. And then run it. And assuming that we haven't forgotten anything, this is going to be bending down and coming from the other side. So let's look at the deformation. You can see that this end is welded. You can see that. That end is coming out. You can see if you animate it, you can see it's coming out of that edge. So I've done this problem two ways, without the plane of symmetry and with the plane of symmetry. So now we're going to solve a problem which is called the shrink fit problem. Suppose we have two pieces. The outer one is made out of steel and the inner one is made out of brass, and the diameter of the steel, inside diameter of the steel, is a little bit smaller than the outer diameter of brass. And I want to put this brass and stick it into that piece of steel. Because the diameters, this diameter is bigger than that hole. The only way you can do that is either force it by a hammer or heat this up so it expands, put the brass in there, let the system cool down, and the steel is going to surround this brass and hold it. That's called shrink fit or pressure fit, and that's what you're going to do. Now, first of all, if these are finite height, okay, then there's no problem with what's happening at the top and the bottom are just free. But if this is a long pipe and this is a long pipe, I'm trying to put this long pipe instead of that long pipe, then you have to be careful when you model the problem. You have to assume that this top face and the bottom face are on surface sliders. This surface slider is not because of symmetry necessarily, it's because of the fact the whole thing is repeated, so everything behaves the same way. So in a sense, there shouldn't be a difference. Now, if these are rings of a specific height, then the same thing applies, except that you don't put surface slider on these top faces or the bottom faces. However, there will be a plane of symmetry halfway through the thickness. So if I assume, for example, the thickness just hypothetically is, I don't know, maybe 1 inch, then I have to take half of this height. I have to take half of this height when it comes to modeling. The other thing is, this is one of those problems that can actually be analytically solved, and the hoop stress and the radial stress are showing here. So this is in the brass, this is in the steel, starts at 0, ends at 0, but it's continuous. But the hoop stress is discontinuous at the interface. So this you should be aware of the fact. So what I'm going to do is I'm going to solve this problem. But also, you see that you can take any sector. You can take a 30-degree sector, 45-degree, 90, etc. So I'll take a 30-degree sector, okay? And what I'm going to do is I'm going to create two rectangles of the appropriate dimensions and then shaft it to get my geometry. Okay, that's one way. That's one way of doing it. So let me go at here. Let's do the brass first. We don't need this. We don't need that. We start with the product file. Product. Immediately we save it. So file, save management, save as, one level up. I'll create a folder called shrink fit. Shrink fit or pressure fit. Okay, let's do the brass first. So insert a new part in there. I'll call it brass. Properties, I'll call it brass. And brass. Okay. Let's make it. Double click on the brass on a convenient plane, on that vertical plane. In my case, YZ, I will sketch a rectangle, but half the height. Remember, I use the half the height because I know that there is symmetry and I'm dealing with the rings basically shrinking inside of each other. So let's dimension these things. Let's see now. This is going to be 1/2 inch. 0.5. Okay. And dimension from here to here. This is the inside radius that seems to be 2. Sorry, 1. This is 1. This is the inside radius. And the outside radius from here to here is going to be a little bit bigger than 4. So it's going to be, the diameter is 4.002, so the radius is 2.001. So the radial interference is 0.001. So this is the brass exit. And then you revolve it, or shaft it actually. Shaft that sketch about the z-axis. I think I said I take 30 degrees, so let me do that. First angle, 30 degrees. This is the first angle right there. There. And I'm going to change the color of this so that you can see it better. Properties. I'll change this thing to yellow. Okay, the other one, we leave it the way it is. Okay, good. All the way to the top. Oh, wait a minute. In this brass, sorry, apply material to it. We have to be in the brass. Apply material. Brass on that part. On that part. We say okay. So that part is made out of brass. All the way to the top. Save everything. Okay, so insert a new part in there. Say no. And I'm going to call this thing steel. 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 This is the part name down here. The other one is the instant name. Okay, fine. Double click on steel. On that same plane, same vertical plane, I will sketch. This time another rectangle. Put the right dimensions there. So the distance from here to here is going to be 2, a little bit smaller than that 2.001. Okay. And the distance from here to here, according to the drawing, is 2.5. Diameter of 5, yeah, 2.5. Radius 2.5, diameter 5. And the height here is the same as the other height, which is 0.5. 0.5. And then we say OK. Say OK. Exit. Revolve it about the z-axis. Once again by 30 degrees. 30 degrees. Say OK. Good. And let's make it out of steel. So apply material, steel. Good. All the way to the top and save. Okay, good, good. So now we're going to go to start analysis and simulation, generative structure analysis. CATIA sees two solid elements. It meshes them immediately. If you want, you can look at the mesh, right-click mesh visualization. That's not necessary, but right there you can see. Now notice that there are different nodes, and along that seam there are different node numbers from the two sides. But that's okay. We're going to create a connection between them. All right, so what do we know about surface sliders? So surface slider on this face and that face, and that face and that face, and because of symmetry, this face and over here. If this was a long tube, inside of another long tube, these would be surface sliders too, but we're not doing that problem. When you're done, just cancel it. It's going to go away. That's because of my issue with yeah. So that's good. Now we're going to create a connection. We're going to create a connection between them. So general analysis connection. For the first component, let's hide one of these. Take that surface. For the second component, let's take the surface of the guy that's in hiding. This surface. So there is some kind of a relationship between these two. The question is, what kind of a relationship? That's the only thing. In fact, one is bigger than the other one. You can see that. One way of doing the problem is you look at this face-face connection. There is one of them that looks like that. It says pressure fitting connection property. You click on it. It says, okay, select your support. That means the connection that you created. It's right here, right there. See that? This is the connection that you created. You can select it from here, or you can select it from the tree right there. It doesn't matter. Select that. It says, what is overlap? The overlap is radial interference, which is 0.001. Diameter-wise, 0.002, but this wants half of that, so radial interference. Now, what it does, it goes and resolves this overlap and solves the problem for us. It is possible to do the problem a different way using contact, stuff like that, but I'm not going to do it. I want to show you how you use this thing to begin with. Okay, good. So let's save the analysis. Files, save management. Here's analysis, save as, in that same folder that I called the shaft. No, not here, not shaft bearing one. I did create something called shrink fit, didn't I? Thought I did. Oh, shrink fit right there. So it puts it there because my part and product are there. Remember, on a furniture, on a test, if you give me analysis of an assembly, you have to give me the product, all the parts, and the analysis. Any one of them missing cannot be marked. And now we're going to run it. Hopefully everything is going to be reasonable. I didn't forget anything. That's fine. And let's look at it. You click on it. That's how it looks like. You might say, wait a minute, what's going on here? What's going on here? These are supposed to be in contact. Remember, the brass is being squished in. The steel is being squished out by tiny amount. So if you magnify it so you can see, it seems that this is going in, this is going out. But this is because I magnified it. We say, fine, don't do that. Show me the real scale. The real scale, you go and click on the amplification magnitude and just put 1. This is the real thing. And of course, if you animate, you can see nothing. So if you you can look at the von Mises stress, for example, here. You can look at the displacement if you want, or you can look at the von Mises stress. Where is it? Right here. And again, you change the scale so that you can see something. Scale of 1. We say, okay, change the rendering. There should be sharp discontinuity at the seam. And it is. Because remember, the hoop stress is discontinuous, and therefore von Mises stress is going to be discontinuous. Now, remember, the reason that when you do these things, if the radial interference is too big, then it makes this material yield and that material yield possibly. So that's how you use these von Mises stress, for example, because if it's too small, that's fine. If it's too big, material will yield. One thing that is of interest is pressure contact pressure. If you double click on this, and on the selection you say pressure, let me see if I can plot it. Not that one. Okay, so let me go ahead back. Hang in there. So let's say all, first of all. If you look at if you look at one of these, for example, if you look at just the outside one, the steel, you can see the pressure distribution here. Or if you want to see the brass, this one's steel. You want to see the brass by itself, there it is. Okay. And it is also possible to plot the pressure distribution on this, but let me, if you want to see the pressure on that interface, one way to do it is the following. Let me deactivate this first. Deactivate that. I'm going to change the rendering here. I don't like this. Okay, good. So I'm going to say create a group. Remember the group stuff that we did, and I closed it here because I wanted to clean up the screen. So view toolbars. Let's see if you can find group somewhere. Groups right there. It's right there. And I'm going to do a surface group. One of these is a surface group. This is a point edge surface. And I'm going to hide that. And I'm going to say, okay, give me all the stuff on that surface. And then we say, okay. Good. So let's activate the von Mises stress. Okay. Double click on it and say, just show me the surface group. All right. And I don't want that guy. Say, okay. And change the rendering to material shading. You can see color. You might say, what the heck is this? Well, first of all, notice that the pressure is almost constant. Now when you get to the ends, because this end is free, of course, the situation changes. But in here, the pressure is almost constant. That doesn't surprise. So this is the von Mises stress distribution on that surface. Okay? If I wanted to see it, I would have to hide for example, the brass or hide the steel. I would see the same thing. But this is an alternative way of using this group feature. All right, folks, that takes care of it. See you next week.